Okay. I'm showing you here kind of the flow of execution. So this is a program. This is a simple assembler program. It loads A, okay? Adds 7 to it, stores the result in A, and compares it to 56. Okay? Branch not equal to loop. So if it isn't equal to 56, it branches back. This is just a simple little program. It says, okay, I'm going to do this, just to amuse us. Okay? What I'm interested in is, at some point, coming along here, at this point right here, actually, a printer interrupt happens. Okay? And immediately, it does the add, finishes that, does not get to do the store. And it branches over to a different location of memory where this code, part of the device driver, is stored. Okay? Push of the PC, Derek's talked about stacks, right? Derek has talked about stacks. Yeah, okay. So it pushes the program counter onto the stack. That's the thing that's deciding, okay, program counter is pointing at this instruction, this instruction, this instruction, this instruction. What happens is here, when the interrupt happens, it actually saves to the current program counter, so it's now pointing here. Okay. This guy. Saves that and replaces it with this, the program counter pointing at here. Okay. So that's an interrupt happens. Poof. So far so good. The interrupt happened because the printer was done doing something, and it now wants to carry on doing something else. So in this case, here's a device driver, code in a device driver. I push the accumulator, because why do I push the accumulator? Because that's when I say add 7, load A, add 7, it's storing that stuff in a register called the accumulator. Very simple machine here. So I need, this number is going to be, say, 14 at this point. I need to keep that. So I'm going to say push the accumulator. Then I input from some I/O location, which I made up here. And that's, the assumption is that's the status register for the printer. Okay, so I'm reading the status. Load the printer status. Branch not equal to error. So if there was an error, I'm going to test Q. So I'm going to see if the Q is empty. Branch equal to done. It's empty. Okay. Load add Q, so load a value from the Q. Output it to the output register for the printer. Pop the accumulator and return. Carry on with a normally scheduled program. Okay. Simple as that. That's what interrupts do. Now, to add a little bit of complexity to it, okay, it doesn't actually go directly to the device driver. It goes through, it really goes through what's called an interrupt vector. Okay, so this will be 1, 2, 3, 4, 5. So this is a table. And let's say, and the printer may be in, printer is interrupt 2, okay? And the keyboard is interrupt 3. I'm making these up. And some of the disk drive is 5. So what it's going to do in the case of the printer is it's going to branch through here. It's going to branch to this. Okay? And in here, there's code that says branch to wherever you loaded the device driver. And that makes it a little bit more flexible because I can have this, modify this table and change things in the table, and then I can move this stuff around anywhere in there. So this is one level of indirection here, which I should point out. Okay. And this table is hardwired. It's part of the design of the machine. So it's actually memory, which I can read and write, but it's built into the machine where it's going to branch to. Okay. This is not code that somebody wrote. This is actually part of the architecture of the machine. The interrupts are hardware, and where they're going to jump to is part of the hardware. So goes to there, does its thing, returns back to here. Any questions about that?